Indiana University East, Department of Science, Standard Electrode Potentials, Basic Concepts. So to understand what is going on here, we need to start by looking at cell EMF, the cell electromotive force. And your electrons go from the anode to the cathode in all cases. And so the electrons must be flowing in such a way that basically you have a higher potential when you started to finishing, just like you have on a waterfall. On a waterfall, you have a higher gravitational potential energy here, and it goes down and has a low potential energy. Similarly, you have a higher potential energy here to a lower potential energy at the cathode. This difference in potential energy can be captured in the cell EMF, which is the change in energy is the energy per unit charge. However, one thing we have to consider is the fact that we have a lot of different combinations of anions and cations. Okay, if you look at the list of standard reduction potentials, you see a lot of different half reactions we can use. I have like 33 or 34 on the list, I think, depending on which list you look at. At least there's one that has that many. And guess what? We can couple any of them with another one, and you have a lot of combinations. So if you have that many combinations, you have that many different potential cell potentials, and who wants to list them on a table? And you can't reasonably do that. Add to the fact that there's also concentration effects, okay, and temperature effects. Now temperature, we're going to just assume we're at 25 degrees C, but we still have to deal with different concentrations of cells. So how do we handle this? So basically what we want to do is to set some set of conventions such that we can just look at what we have and simplify the problem of tabulating everything. And we start by using standard conditions. 1 molar solutions, 1 atmosphere partial pressure for gases, and we're going to assume we're at 25 degrees C for the purpose of this course. And then the second thing we can do is actually look at if we have oxidation reduction, right? But oxidation is really the reverse of a reduction reaction. However unspontaneous it is, we can still consider it that way. So by convention, we look at reduction potentials only. Thirdly, we still have these potentials, but let's think about this a bit. Really, in terms of spontaneous directions, we are talking about Gibbs free energy. Okay? If you look at Gibbs free energy, we don't know the exact values. So we have to define some sort of standard. And in case of electropotentials, we define the standard hydrogen electrode with H plus being reduced to form H2 with a platinum electrode. This is what we call a standard hydrogen electrode. And this reaction is defined to have a standard reduction potential of 0 volts. So here is a list of standard reduction potentials typical of those you find in a book. Different books have slightly different lists, but basically you're looking at the same big picture. There is no point memorizing all of these. You will be given them in an exam situation in my class. Okay? And furthermore, you don't try and copy this down, because there's actually nothing. It's just, I don't think you can squint and look at it, but you need to be able to use it. So a few comments. I think the first comment is, what if we had to multiply the coefficients? Right, there are coefficients here, electrons, but remember the definition of electropotentials. The definition of electrode potentials is the energy per unit charge. So therefore, the number of electrons has been taken into account. And so, when you multiply by stoichiometric coefficients, the reduction potentials do not change. Changing to stoichiometric coefficients does nothing there. Number 2, they're typically listed with things that reduce the most easily on top. So you've got fluorine going to fluoride at the top, and vice versa. At the bottom, you got things like K plus going to K. We're listing reduction potentials. So what we're not doing is listing any oxidation potentials. So oxidation reactions, remember, you can go backwards. And the way we do these calculations is going to take care of this. And what you can do here is, when you do this, you're going to take your cell potential can be taken as difference between that at the cathode and the anode. So the cell potential is the reduction potential of the cathode minus the reduction potential of the anode. A common mistake made by students is that you think that you have, because oxidation occurs at the anode, you swap it. No. You're using reduction potentials here and here. And the minus sign here takes care of any reversal of the reaction. So for example, here I have zinc going to zinc 2 plus as my anode, and here I've got the standard hydrogen electrode as my cathode. Okay, and so this, our cell potential is 0. Our cell potential for this is minus 0.76 volts. So remember, it's cathode minus anode. So the standard hydrogen electrode, 0 volts, minus the anode, so zinc going to so Zn2 plus. I don't actually change the sign of this, I just put in minus 0.76 volts. So minus minus, so I get the standard cell potential to be 0.76 volts.